we have seen where the linearity comes from. It is basically the linearity in the parameters W. The general regression problem, however, is that you want to find f star that minimizes some error function in some search space of functions. So far, our calligraphic S has been all the functions that are linear in some basis functions W, and this is exactly what we have dealt with. A parameterized form, where specifically the parameterized form is linear W transpose phi x. So in summary, this is what we have dealt with so far. We have dealt with the simple least squares objective for this linear function, and in the last class, through two different routes, one is through geometric intuition, geometric reasoning, and the other is via gradients, right? So we saw this or derived this using the setting of gradient of the error function to 0 and geometric reasoning. You will see more of gradient now. Geometric reasoning beyond a point will be very difficult to generalize. Okay, so this is a summary. Also important to note what we mean by this matrix phi. This matrix phi basically refers to examples x1 to xm organized as rows. So each row is an individual example, whereas the columns correspond to the features. And each row is an example featureized. Okay, now we will move on to nonlinear fitting. And at the end of last class, I said, well, this is something we will get into now. So the phi i's are attribute basis function. Let's say that my example x is just in the real, is just a scalar, okay, real scalar. So if I tried an fx equals wx plus b, which is nothing but wb dot product with x1, right, we basically get the linear fit that we began. And in fact, today I will take some sine function. Let's say this is. So my linear fit will look like this. And now I may want to make use of the fact that the phi's could be designed arbitrarily to suit my purpose. So can you give me a choice of phi's that would probably help me fit these set of points better? Certainly, I mean, doesn't look like a linear fit is the best choice. You could have probably got a quadratic fit to do better. So quadratic fit would have looked like this, or actually sorry, it wouldn't have looked, they won't have in a second curvature, but yes, it would have looked like this. Okay. In general, I could have had a polynomial fit these set of points. I have actually synthesized these set of points as a subset of the y basically is for a subset of points with respect to the sine function. I could have gone ahead and actually it would have looked completely nonlinear. So I would, and you know that you can get arbitrary levels of precision fit using Taylor series, right? And Taylor series gives you polynomial expansions. So let's say I want to fit polynomial functions. So I'm very specific now. My nonlinear function should be polynomial. So can you suggest some choice of phi 1 to phi p? I mean, I showed the quadratic case. I could get more ambitious and say, well, I also want cubic approximations. So can you help me fill up the phi, the capital phi matrix? C. So he's suggesting that the phi looks like Cx. So Qx. Oh no. Qx cube you meant. Okay. So x, you're saying x. Okay. This is for x1. You want to put in coefficients here as well? Okay, so should you put in coefficients here or no? I know that my cubic fit would look like ax cube plus bx square plus cx plus d. But what do I expect a, b, c, d to be filled in from? The w, right? So I would expect that a is say w4, b is w3, c is w2 and d is w1. Okay, so I try to be consistent with that notation and start with 1 here and move on to higher order coefficients, higher order terms. That's exactly what we'll fill in there. 1, x1, x1 square, x1 raised to p minus 1. So the correspondence I have drawn here is that phi p phi p xm would be xm raised to p minus 1. So sounds attractive, and let's see what the implications are. We'll try and do the fit. Okay, so these are the different fits. Power 1 is what we started off with. This is for the red points are basically coming from some sine function for a subset of interval, a small interval of x. So linear fit we are not too happy with. Okay, I have not shown the quadratic fit, but quadratic fit would look something like this. It will not have two curvatures. I mean, it will just be one curvature and then, in a sense, it will just turn down once and then it will not turn up again. This is for power 3, it turns up again. Power 6, okay, and power 9. What is your observation? What do you observe as p increases? P is a power. Yeah. Okay. So are you happy with P equals 1? Certainly not, right? So at least give credit where it's due. So it learned to fit the points better initially, right? What you also pointed out that while we are able to fit points better as P initially increases, subsequently as for large values of P, you are also learning to fit the noise. Okay, so this is the function we are talking about with least squares. Objective is still least squares. Now we'll have to, yes, so we have to do that eventually. For the time being, so to actually get into modeling noise, should we use probability? For us, probability is the way of fitting, right? I mean, what is noise for us? So it doesn't seem to belong to the family of points that you have actually you have obtained, right? So it doesn't belong to the distribution that the data would have come from, or it belongs with very low probability. So noise needs probability treatment. But let's just proceed assuming that what appears to be noise visually is actual noise, in the sense that we would have expected, or rather, I mean, all these points don't have to be taken seriously. We expected some canonical set of points in this cluster to be good enough, whereas as you proceed with large values of the power, you find that you're basically tending to take all of them too seriously. Now, how do you know that we land up fitting noise as well? Is there some indication? Let's just look at this function, right? So what happens for polynomial? For polynomial, what vanishes here? Sorry, for quadratic, what vanishes here? Okay, so these, so W4 equals W5 equals 0 for quadratic. W k to Wp minus 1 equals 0 for the kth order fit, right? For degree k fit. This is what we know. In general, Wk to Wp minus 1 will all be 0 for a degree k fit. So what is your indication of whether you are taking the noise too seriously? One indication, many of these higher order W's will not become 0, they start assuming some magnitude, right? In fact, you would like that the model only consumes as much W as it should, not more than required. Just because there is an extra paratha left, you don't kind of gobble it up, somebody else could eat it. So you would like the model to be sane and social, civilized in its behavior, but looks like these models are not very civilized, right? You give it parameter space to search, it says I'll eat a little bit, I'll nibble it off and make it unedible for anyone else. So that's what we are not happy about, right? And that's one way you can articulate your unhappiness. But let's try and do this a little bit more kind of empirically. So what we are doing here is we are actually fitting the W's, we are just plotting the W's. So intercept is basically W0, I mean, so the W1 to WP is not necessarily the same numbering as there, but you can understand that this is the W1 I talked about here, this is our W2, right? So for model with power 1, you will find that the first two are 0, the first two are non-zero, then basically NN, this is supposed to be 0, so let's just understand that these are 0. And as I proceed, to higher order, high degree, you will find that more and more of the W's become non-zero. Okay. Now one way that you can measure that lots of W's are becoming non-zero is through, how do you measure that W is becoming, I mean lots of components are becoming non-zero. So overall the magnitude of W is increasing. In fact, I could do that. I could plot, I could also plot, I have done that here, but I could also plot the norm of W. I probably forgot to do it, I'll do it later on. So what you observe is that as W increases, as the degree increases, the norm of W increases. And let's refer to the 2 norm to begin with, though this can hold for other norms as well. So the norm tends increase. Why? Because more or increasing number of non-zero WIs. Okay, so this is what we are talking about. As P increases, W star norm W star tends to increase when W star is a least squares fit. This is important. This may or may not hold for some other fits that we will talk about, and we are basically motivating those other fits right now. But I can say this for W when it's the least squares fit. This is a summary so far. So as we proceed, you will get more ideas. You'll also lab, you'll get to see this yourself, and yes, you could prove under certain settings. Okay, so what we have discussed so far is generalized into ridge regression. So what we have is a special case of something called ridge regression. And what happens in ridge regression is that you penalize the fit, the magnitude of W after the fit. Right? So you want to ensure that as you are trying to minimize the sum of squares error, you also ensure that the magnitude of the W's remains small. And here specifically we have chosen the 2 norm of W. We will see that we could also handle other norms. 2 norm is attractive because you could compute gradients easily. The function remains differentiable everywhere. We also refer to this as a penalty function. Later on, we'll often use this omega to denote an arbitrary penalty function. Okay, so hope this simple motivation is clear. What is the motivation? As you increase the degree, you are letting multiple W's become non-zero. Overall, that will contribute to increasing magnitude of W measured in terms of some norm, specifically 2 norm. So that's certainly one motivation. Okay, so motivation 1 is empirical observation backed by intuition. Okay. How many of you are unhappy with this much justification? Be honest. You don't like this hand wavy justification. Okay. So how many of you others seem to be very happy with this hand wavy justification? So can I have other support as well? Or do you want to stop this discussion here? So you would like to proceed, right? And understand, well, is there some mathematical underpinning? Okay, so there's the other justification, which is a probabilistic interpretation, and that we'll now build upon, and will also lead to Bayesian estimation inference. So what this will do is give you some probabilistic understanding of why this component makes sense. Just because I want to suppress, I don't just add a component. And why do I add it in a linearly additive manner? Why is it plus? Why don't I multiply the sum of square error with a 2 norm of W, right? Why is additive and not multiplicative? So you can have multiple questions. Now it turns out that while we defer the justification to a few slides later, the solution is actually very interesting as well. So if you solve using the gradient, right, basically set the gradient to 0, you get this interesting form, and let's contrast this form with the previous one. Okay, so W least squares was phi transpose phi inverse phi transpose y, and W ridge is phi transpose phi plus lambda I inverse phi transpose y. towards the end of last class, what did we argue about phi transpose phi and its invertibility? If phi is full column rank, so phi transpose phi is invertible if and only if phi is full column rank, right? Now if phi transpose phi is not invertible, which means if phi is not full column rank, is that possible? Is it possible that sometimes by mistake two terms will start looking the same, right? You're almost sleepy in the night, you're just trying to complete your assignment in a rush and you use the square term twice. Possible? So for that small mistake of yours, this guy becomes non-invertible. So regression says, well, I'm going to basically increase the, so we'll see the way what this lambda I does, but it increases the chances of invertibility of phi transpose phi. It has implications in terms of eigenvalues. There's an increase in the value of eigenvalue and so on. So again, I think a tutorial there will be some more discussion on this, but for the time being, the solution also looks a bit attractive. It can help you handle non-invertible cases, right, or rather full column rank cases. Now it turns out that the machinery we have developed so far could also be used for other regression models. Like ridge regression was a generalization of linear regression. You could also adapt the linear regression model so far for classification. And again, a little later we will discuss this part, but logistic regression is the regression model that is often used. It's a very nice, attractive model for classification. And whereas regression was trying to fit points or prediction based on inputs using linear or whatever polynomial fits, in the case of classification, you want to ensure that points labeled positive can be classified or separated from points labeled negative, and again you want that to be through either linear or polynomial or whatever other fit. This is the case of classification, and it turns out that the core model still remains this simple thing, B plus phi W transpose phi x. That's the core engine. But now the core engine is used to define a probability function, rather the log transformation of a probability function or the logit of a probability function. Logit is basically log odds. Okay, so log of class probability of y given x divided by 1 minus probability of y given x. That is called the logit function. This logit is basically logit p is p divided by 1 minus p, that's it. So this, if it turns out to be the linear function, then you are able to deal with classification as well. And here again your phi could become, phi could be defined using any linear interpolation of the different x components in the original input. Okay, so this is how you could build on whatever you have discussed so far, and that's why linear regression is very fundamental. What I'll do next is focus for some time on the probabilistic interpretation, because that's what will give us a lot of ammunition. And as you can see, even to get to logistic regression, we need to be able to deal with probabilistic modeling. This is very, very vital, whether you want to understand the norm W square or not. But I must warn those who are catching up still not brushed up probability, please do that soon enough. Okay, so we'll have to now basically use probability, and there are also other models, lasso regression, stepwise regression, and several others. So we'll get exposed to many of those. Any questions? Yes. Lambda is called a hyperparameter. It's called a hyperparameter. So I can't avoid writing on the slides just because the board space is actually quite less. So I could probably make use of the white part as well, but I'll try and write sparingly on the slides. Okay. So let's build on probabilistic interpretation, and then also we'll look at more efficient algorithms for solving. We had to resort to closed form solution. We could get a closed form solution and resorted to setting gradient to 0, and also the geometric interpretation of the solution. But we want more generic tools which can help us solve the objective functions, the minimization problems that we might set up for ourselves. Okay. So probabilistic view of linear regression, and as I to remind you, this is going to gradually help us understand why we would insert a lambda I right here, or why we would be interested in an objective function which has this lambda 2 norm square in addition to the least square component. Okay, so given a training data set of m points, what we are going to assume is that each target yj is drawn from a probabilistic model. So for us the entire data has come from some underlying probability distribution. I don't know the exact probability distribution, but I am going to make some assumptions about the form of the probability distribution. Right. So if you think of the form of the probability distribution as a class, you are all familiar with object oriented programming. So think of class as the form of a probability distribution, and an object as an instance of that probability distribution. We all know that an object would be an instance of a class, and here we are talking about the form of a distribution that we assume would have generated the data set. Now what we want to do is, well, what is the specific configuration, some value of w's, parameters, that most likely generated the data set. So we are trying to discover this instance, right. So starting here is where we are kind of assuming the form. what are we saying? Well, W transpose X. For the timing, I'll drop the phi and just use X. At times we'll do that just to simplify notation. Is really for notational simplification. You could put back the phi. So what we assume is that in addition to the transformation W on X, there is some additive noise, stochastic noise, a probabilistic noise. Right, that's modeled as a random variable epsilon J. Now most of our probabilistic modeling will be with respect to epsilon J, and that will have its implication on the form of the distribution associated with Y. So if I toss a coin, the coin has some probability of heads and tails, and now if I toss a coin 20 times, the number of heads that I get out of 20 tosses, does that also have a probability distribution? Yes. So I start with a single coin toss which has a probability model. That probability model will translate into a probability model for the number of heads in 20 coin tosses. And if I do that with 20 different coins, and the number of coins which have the same number of heads out of 20 coin tosses, would that also have a distribution? Yes, right. So you can derive distributions. So for us, the starting point is a distribution on the random variable epsilon J. Okay. Now what would you expect? You should make the least possible assumptions, or rather not more than absolutely required. So epsilon J's, what do you expect the noise across multiple Yj's? Do you think they should be correlated in the broadest setting? Well, you could consider correlations, and that's the topic of graphical models. But we'll begin with completely uncorrelated. So that the epsilon J has nothing to do with epsilon K, other than the fact that they come from the same distribution. So the epsilon J's will be identically distributed but independent of each other. Okay. So epsilon J will be identically distributed as any epsilon K, yet epsilon J will be independent. Will be independent of epsilon K. Okay. So these are kind of constraints we are putting on the form of the probability distribution. Again, I will not be able to expand everything on board. So this is IID epsilon J's. IID is independent and identically distributed. Okay. These two together are abbreviated as IID. What else? This makes sense, but can I have some more specific form for the distribution of epsilon J? Right. Epsilon J to have 0 mean. What else? zero mean, we would expect that errors cancel out in the asymptotic sense. Lots of samples we had, they centered around mean 0. Yeah, but as part of the assumption, his point is, I'll just repeat questions. So his point is, even if they were not centered around 0, we could center them around 0. But then you'll need to work harder to find out what they are centered around. Okay, so let's make this simple enough. And then what else? What about the form of a distribution? So, what about the variance? We expect some variance, certainly not 0, otherwise there's no point discussing about a distribution. At the same time, the form should be such that given a variance, I am making the least possible assumptions about the form of the distribution, because there is noise after all, right? So it turns out that there is a distribution called the Gaussian distribution, which for a specified variance, I will elaborate on that, is the most unconstrained, or rather has the highest entropy. Okay, you've come across entropy. So what is the entropy of a random variable with a particular distribution? Put an integral. I am assuming it's a continuous random variable. Okay. So what we are going to claim is that if I am specified as a variance, some constraint on the variance, and I've left open the form of P, that form of P which will obey the variance constraint and yet maximize the entropy is the Gaussian distribution. So and we will use that for as a third point, epsilon j to have 0 mean and normally distributed with mean 0, variance sigma square. So Gaussian and normal are used synonymously. Okay, I've written this very roughly, but let's get more specific now. Okay, so this is what we have about the form of the distribution so far. IID epsilon j is to have 0 mean and normally distributed with mean 0, where some variance sigma square. So high entropy is chaos, which means least possible structure, least possible assumptions constraint, right? Okay, so let us model the noises coming from a Gaussian distribution, and in addition we'll have that epsilon 1, epsilon 2, each epsilon j while coming from the Gaussian distribution that is being independently distributed. This is what we mean by identically distributed. So while being identically distributed, we'll also assume the probability of epsilon 1 comma epsilon 2 is probability of epsilon 1 into probability of epsilon 2, and probability of epsilon 1 given epsilon 2 is probability of epsilon 1. You understand, right? This is what we mean by independence. Okay. So the IID is coming from the independence and analytical distribution. Also, we'll assume that the so they will not assume any covariance across the epsilon j's. I mean, this also will result. So covariance of epsilon 1, epsilon 2, or epsilon I, epsilon j will be 0 for all I not equal to j. This will result from the assumptions made so far. Okay, so now it turns out that when we try to maximize this log likelihood, so now I'll explain what log likelihood, but turns out that the solution is the same. This is the summary of where we are heading. Phi transpose phi inverse, phi transpose phi. This is exactly the least square solution. So under these assumptions, if we try and maximize the likelihood, a log likelihood, we get the same solution. Okay, so what we will do next is show this and also explain likelihood, also log likelihood. So in this process of different views of linear regression, we are also exposing ourselves to more tools which will be required for this course. Okay, so now how does this happen? The first step, as I said, is if I have a probabilistic interpretation on the coin toss, I also have a probabilistic interpretation on the number of heads across 20 coin tosses. Likewise, epsilon j being normal, mean 0, variance sigma square will mean that yj will be normally distributed with mean w transpose xj and variance sigma square. I would like you to work this out as an exercise. To derive, you just need to recall what is the form of normal with mean mu and variance sigma square. What is this form? 1 upon sigma under root 2 pi e minus of x minus mu square divided by 2 sigma square. So all you have to do is use this form, and then the rest should follow. The distribution of y will follow. You can do simple things. You can also assume that if you add a constant to a normally distributed random variable, the sum will also be a normally distributed random variable. And if the sum is normally distributed random variable, then you can work backwards what the mean and the sigma square, the variance square should look like. Okay. So there are multiple ways you can work out, but this is the basic form you need. Now the objective that we will derive, that will employ to find my W is the maximum likelihood estimation. Okay, so let's say I observed my data set, the probability of data set, right? What is probability of data set? Probability of data set is probability of y1 ym comma x1 to xm. I already observed this data set. Now since the epsilons are independent and analytically distributed, can I say that the y's are also independent and analytically distributed? They are independent of each other. I can show that, but we'll use common sense here. They are independent and identically distributed. So because of this, I can write this as product over I equals 1 to m. Okay, so I'm actually more specifically looking at the probability of y1 to ym given x1 to xm. So let's be specific, because x1 to xm is already given to you. So we are looking at the distribution of y's. So this can be a product over the individual probability of yi given xi. And that's also the form we have written here. The form here written here is nothing but probability of yj given xj. That goes without saying. You should be able to understand that by looking at the form. Okay. So now this is when we know the parameters w, right? So in some sense I put a subscript w here, because this product I will obtain assuming some value of w. In fact, not just w but also sigma square. Sorry, the sigma square is given to you, so it's just w. Okay, so this is the probability of the data set, or the probability of the y's given the x's. What maximum likelihood estimation does is says, well, you fixed the w's, got the y's, let's turn things around. What I have observed are the y's. What I have observed are the y's, and I need to work backwards on the w's. So the same function is called likelihood when you view it as a function of w given the data set or subscript the data set. It's the same, the probability of the data assuming some w, view that through a different lens, view it as a function of the w where the data set is given to you, and that will be called the likelihood function, right? The likelihood of the parameters, or rather the likelihood value associated with the observed data set when I evaluate it for one set of parameters. I change the set of parameters, the likelihood will change. So that's how it's a function of the parameters. Just going back to what we've been showing. So I plot these points, I have the points already, which means I have the data. Now for different w's, I'm trying to find out which fit is the best. So that's how I'm trying to maximize the likelihood. So more generally, set of IID observations y are generated according to a probability of model parameterized by theta. Theta, for example, theta is w for us, and you're looking at yj given xj, right? So the problem we are interested in is w star, MLE, maximum likelihood estimate, is the parameters w that maximize the product, the same function as we showed in the previous slide, of yj given w transpose xj comma sigma square. This is what we mean, and this entire product, this is called the likelihood function. Likelihood w or likelihood w given d, either is fine. Sometimes people put d also in the subscript. All these are fine, but it should be viewed as a function of w. So what we will see is that this solution, the solution to this will be the same as the solution to the maximizing of likelihood. Of course, we will come to this later on. I'll erase the additional component here. We will look at the simpler one. It's called the maximum likelihood this was called the least squares fit, and we'll say that they are both coincide. But this likelihood is being computed under certain assumptions. What are the assumptions? The form where epsilon is normally distributed, mean zero, variance sigma square, IID, and so on. Under all those assumptions. So again, I would like to remind you, PR of y given theta is probability of y, probability density at y, when observed as function of y, and it is likelihood when observed as function of theta. So okay, so let's get to how would this change the parameter estimation. If you, instead of taking the likelihood, which was defined to be a product over all the examples, so suppose we, instead of this product over the normal distribution, what if we tried the log? Okay, so typically the idea is you maximize log likelihood instead of likelihood. Why is log interesting here? A log of product will become sum of logs. So my claim is that this is the same as argmax log of the likelihood, which turns out to be argmax of sum over the examples of the log of the normal distribution. So question is this correct? Can I just equate saying that the W that maximizes likelihood is the same as that which maximizes the log of the likelihood? Okay, so you can show, so in tutorial 1, problem 4 I guess, so here's the claim, maximizing monotonically maximizing monotonically strictly, so I should put this strictly also, strictly monotonically increasing function of an objective is the same as maximizing the objective. Okay, so if I had a function that is like this and I subject it to some monotonically increasing function. Okay, so let's first of all quickly see that log is strictly monotonically increasing, right? So if I subject this to a log or any other strictly monotonically increasing function, the point of maximum, the function will change, obviously. It may dampen out a bit, but the point of maximum, if it were x star, the point will still remain x star. That is a claim. Let me use W here to be more consistent. So you'll have the maximum at the same point W star. That's what we mean by equivalent. So this W star will remain the same, which makes sense intuitively, right? And monotonically, because I mean you don't want a non-monotonic. I mean in the sense it may be increasing, but if it makes things flat at points, then you will not be able to recover the original solution. So if it was increasing strictly, then you are fine. You can recover back. So again, makes intuitive sense. You can try and prove it. It's part of the tutorial. So if the translation was not monotonic, so if this became, okay, if this became, sorry, this was like this, if this became like this, beyond a point I just flatten it out. If this was my W star, now I have an entire range of W stars. How will I recover my original solution? So it should be strictly for that reason. And very often when we say monotonically, we mean strictly. I think in calculus that strictly is often implicit. Sometimes you have to say monotonically non-decreasing to mean it's not strictly increasing and so on. So the short answer to this long question is no. This will not affect the parameter. Why apply the log transformation? That's obvious. Simplicity of computation, right? So your product becomes a sum, and in fact you get a sum of logs. It's more than that. Log of product becomes sum of logs. Okay, so with all this, this is our MLE, the generic expression for the MLE estimation, and it's interesting that because we are dealing with independent and identically distributed examples or the epsilon j's, that's why we are able to do this decomposition, sum of logs. This is owing to IID, the summation, IID assumption. That's what I showed you. Okay, now let's complete the story. If you try and expand the n, do you think you will get this form? What does n have? N with the yj, w transpose xj. What does it have? It has exponential, it has this exp part where we have written there, right? So let's just look at this specific form. Everything else is a detail. We'll have log of, forget the other multiplicative constants, log of exp of, right, but let's see here, y, so it will be yj minus w transpose phi xj square divided by 2 sigma square minus. So log of exp of this form, and you are summing across all of these, right? What will happen? We will basically get a summation of yi minus w transpose phi xj, what w transpose xj square, and that will exactly turn out to be this form. Okay, so maximum likelihood estimate under these assumptions will be the same as the least square estimate. Okay, I am going to now move on a bit and now illustrate with respect to a very much simpler example what this maximum likelihood estimate is doing, right? So let's say we toss a coin n times. Each coin toss is a binary random variable with a Bernoulli distribution. What's a Bernoulli distribution? This is exactly this. Probability of yj given theta is q raised to xj 1 minus theta raised to 1 minus yj, q raised to yj, theta raised to. So how would you estimate theta using maximum likelihood estimation? I am giving you a simpler problem so that you can start seeing what all this is doing. Please do this. Let's take a couple of minutes. You are free to apply log transformation because you already seen. If I forgot to mention here. Actually, yeah, there's no IID assumption required. There's only single coin toss. Sorry, there are n coin tosses. So n coin tosses, and this is where IID comes in. the n coin tosses are all independent of each other. So you can bring in the ID assumption. You can assume that out of the n coin tosses, say h some number n are basically heads. Everyone gets this? Summation j equals 1 to n yj minus theta divided by theta into 1 minus theta equals 0. And this is very, thereafter it's very simple. This if this has to be 0, this implies you are summing theta how many times? N times, right? So this implies that n theta is the summation of the yj's, which I know is how many heads do I have? Capital N. So therefore theta should be theta MLE will be the intuitive, it's basically intuitively m divided by n. All of us have that intuition, it's going to be m divided by n. But all this hard work was to show that maximum likelihood estimation does something which is intuitive. And we have done that using the log transformation. Exactly what we did for linear regression.